So now that you've done machines with springs, and machines with strings, and machines with things hanging from strings and springs with friction, we're going to try and do a machine that has all of those parts all together. So the trick to this is just to start analyzing each piece separately so that you can gather your information and then see what this machine is going to do. Now, if I just start going through the list, I see a thing that's hanging here. So something that's hanging, or something that has mass anyway, is going to have a force of gravity. So I've got my 40 kilogram block, and it is experiencing a force of gravity that way. So it will be 40 times 9.8, which gives me 40 times 9.8, 392 newtons. Okay. And then there'll be a force of tension pointing that way, holding it up. That, whether it's stuck or not, will determine the size of that, so we're just going to leave that for a minute. Then I have a 25 kilogram block here. Now it has mass, so it will also have a force of gravity, mg, which is 25 times 9.8, which gives me 245. Okay, now that block is also experiencing a normal force because it's not falling through the table. So if I look at it, in order to balance my gravity, that normal force has to be exactly this size. So I can deduce then that that's 205 newtons. There's a tension pulling this way from the string that's attached there. And I have a spring back here that's resisting, and I also have friction pushing backwards. So in order to do the friction on that, force of friction, I'll have to do mu times the normal force. And I have a mu labeled there on my table, 0.5. And the normal force is balancing gravity. So it's going to be 245 newtons. For a grand total of times 0.5 gives me 122.5 newtons. All right, so far so good. The only thing I haven't dealt with then is the spring, and spring forces, Fx, are the spring constant multiplied by the amount the spring has stretched. So if I fill in the K, which I have, 1600, what I don't have is this thing right there. So what you're going to be asked for a machine like this is how much would this spring have to be stretched in order to hold the whole thing still. So I'm going to erase some of these diagrams here so that I have some space. But basically, what I've got is a force of gravity from the hanging block, Fg hanging, is 392 newtons. Get rid of that. Then I got a force of gravity for the sliding block, and it was 245 newtons. I used that to determine the normal force on the sliding block, 245 newtons. And I used that, see how these problems are a big long chain. I used that to find the force of friction on the sliding block, which was 122.5. And then I started to do the spring force, which ended up being 1600 times however far that spring is stretched. So if I want this thing to be stuck, then if I add up all of these forces, I should get a net force of 0. That's what stuck means, that there is no net pull this way and no net pull that way. So if I look at this machine, if it's going to move, the 40 is going to drop. So the force that's going this way is this one here from the hanging mass. So I'm going to put in my 392 newtons there. Now, in order to zero out, that force has to beat the friction from the sliding block, and it has to beat the pull from the spring. Now, you'll notice that gravity points this way and normal force points that way, and that is not in line with the way that this machine will move. So I don't need to include these because they are perpendicular to the direction of motion. So the only ones that actually are in line with this machine are the gravity pulling it along, the friction resisting it, and the spring pulling backwards. So I just have to do a little bit of algebra here. So 392 minus 1225 gives me 269.5. If I kick this to the other side, I get minus 269.5 equals negative 1600. And if I divide both sides by negative 1600, let's see what I get there. Gives me 0.168 meters. So if this spring was stretched 16.8 centimeters or 0.168 meters, there would be enough pullback so that it, along with the friction, was able to neutralize the force of gravity from the hanging block. So if you follow this process, this one I left out the amount of stretch, but I could leave out exactly one of these things. I could give you a K and an X, a mu, a mass here, and ask for the hanging mass that would balance it. Or I could give you a K and a stretch and a mass and ask for the friction that was holding it back. Basically, we're just leaving one of these variables unknown and trying to solve for when it would set the net force to 0. So I'm going to erase this and we'll do one more example and then it'll be off to the practice problems. Alright, so looking at this example, I have a K and I have a stretch, so I know everything about the spring. I have a mass for this block, so I can do its gravity. I have a mass for this block, so I can do its gravity. The thing that's missing is the friction. So you notice that there was no mu listed anywhere on this table. So the question that this diagram is implying is, what coefficient of friction would I need in order for this machine to be stuck? So I'm going to start off with my easy forces, my force of gravity this way. So force of gravity for the hanging block is mg, which would be 45 times 9.8, which gives me 441 newtons. I can do the force of gravity on this block. Force of gravity for the slider would be mg, which is 30 times 9.8, which gives me 294. The normal force is going to match this force of gravity, so I can just jot that in there. Normal force acting on the slider equals Fg, which happens to be 294 newtons. Force of friction is mu, force normal. So the only thing experiencing friction is this slider here. So I've got a mu that I don't know, and I have a normal force that I do, 294. And the only force left is the spring force, which is the constant multiplied by the stretch. So my constant here is 1200. And my stretch is 6 centimeters, but I don't put 6 here. 6 centimeters is 0.06 meters. So watch that. 1200 times 0.06 gives me 72. So I'm going to have to look and think about which forces are in line with the motion. So this gravity will cause the string to move. The spring is in line, so is the friction, but the normal force and this gravity are not. So I am not going to need to include that or that in my big long chain. So if my net force is supposed to be 0, I'm going to choose this to be the positive direction. So that's this force is positive, force of gravity trying to pull me off the table. From that, it has to beat the friction, so minus 294 mu, and it has to beat this spring force. So this is very similar to the last setup. I know a whole bunch of numbers and there's one that I don't. So I'm just going to go through the same algebra in order to figure that out. 441 minus 72 is 369. You kick this to the other side, it becomes negative 369. And divide both sides by negative 294. Should give me my coefficient of friction. So I end up with, divided by 294, 1.255. So in order for this machine to be stuck, the coefficient of friction between the slider block and the table has to be at least this. Okay. The practice problems have two like that, where you're solving the stretch of the spring and then the mu that would be required. And then there are two more questions about how much mass this would need and how much mass that would need. But they're very similar. You just end up with one letter you have to isolate and solve for. So good luck.